speeches by Uschi and the group of Center of Applied Energy Research on 2D, what is it? Ceramic nanoweb, sure. Oh yeah. Synthesis for application and catalysis. Please, Uschi.
Thank you very much, Jürgen. Does this work? I'm not sure. The mic doesn't.
There's a small. No, it should work.
Okay. Welcome back after the lunch session, and it's my pleasure to be able to also let you know that we will have another keynote speaker this afternoon. We already had 3 this morning, and Stephen Pennycook will be giving the talk after this presentation. And Gary Jacobs was so kind to switch with me in the morning so that we were able to have the hydrogen, the fuel cell talks, and the water gas shift, John Wagner, Gary, and John Letlow all together. This afternoon we will focus on high resolution TEM work. I would like to introduce to you some work that we have just begun as a collaboration between the University of Louisville, University of Kentucky, and there's a third, a third participant, but Shashank Sharma was still a graduate student. He was finishing his PhD when this work was actually being put out. The work has been just accepted by Advanced Functional Materials for publication, so we're really happy about that. My co-authors are Mahendra Sunkara from University of Louisville. Shashank is now with Hewlett-Packard Laboratories at Palo Alto in California. He got snitched away. We wanted to really have him as a postdoc. And then also my supervisor, Bert Davis. Ceramic nanowebs, what I would like to bring out today is to give you an overview of what this really means, 2D webs. This is a new terminology for ceramics. We named them nanowebs simply because of the very unique way how single crystal 1D structures, these are nanowires, form a web-like assembly that is spread two-dimensionally over a surface. Throughout the talk, I will focus on the mechanism, how these webs form, and also give some ideas on possibly how we might be able to change some of the functional properties. I will then, at the end of the talk, touch on some catalytic applications. What the slides already here. What I would like to say at the beginning is that the work that we will show now is actually based on some preliminary work that was started and performed at the University of Louisville, where Mahendra and Shashank were successful in forming aligned gallium oxide nanowires in a hydrogen-oxygen plasma. And when they said that they formed aligned, I'll give you some idea here. This is what they meant by aligned. They form really like, it almost looks like hedgehogs. There has been a lot of hype lately about nanowires, nanotubes, and everything with nano somehow gets money nowadays. Really. So if you wonder why we have nano all over our titles nowadays. But the very nice alignment of these nanowires here, at the very beginning when I first saw these SEMs, I was impressed to see that oxide structures had these incredible one-dimensional, 1D morphological habit. But then if you look a little bit closer, you can see that there's a lot of other material still present in these samples. There are some random formations, there's lots of gallium still, and one of the reasons is because these experiments were formed from a very large gallium pool. So very early on we had in this collaboration the idea, let's make some materials, some nanowires as catalysts and test their catalytic ability. But in order to do that, we have to selectively grow these nanowires. And that was our very first goal. Just to show you how these nanowires look that formed from these very large gallium pools, they were 1D nanostructures. They were definitely single crystalline. They had very nice X-ray patterns, and we were able to find that the lattice spacings matched those with beta gallium-203 or gallia. What followed then after that was the main idea to design experiments to now selectively form these single crystal gallium nanowires without any other gunk in there, so that we could then use those in the experiments. And we were thinking what type of experiments would make sense. And this is what, in collaboration, talking with Bert Davis early on, made the most sense. To have the overall goal to see what the nanowire study could do if we would look at some systems that have been very well studied in the past. And for example, we're now looking at chemical reactions that provide several either parallel or in series pathways, such as the conversion of a secondary alcohol, where you start with secondary alcohol from ketone and hydrogen, or in another pathway, alkenes and water. But again, now we have to go back and first do our first task and form these nanowires selectively. This is just to give you an overview of the reactor setup. This is an Aztec 5010. This is available right now at the University of Louisville, and this allows us a very nice collaboration. The experiments were done at Louisville, and then we did the research tests, the tests at UK. The sample was placed basically right in here, and let me just show you on the next slide here. Hold on here, there you go. What happened is, instead of using a very large gallium pool, we went ahead and used gallium oxide precursors. The idea came, or was born, simply because we thought that there were so many gallium droplets still in the earlier samples. Like I pointed out, this very large gallium droplet, there were hundreds of smaller ones as well. And what happens is the reactive hydrogen atoms, they will then reduce the gallium oxide and form hydrogen in situ, and you basically have at the tips of the nanowires gallium sitting, reduced gallium. So in other words, we have too much gallium in there. So we wanted to start with a sample where we had a very strong control on the amount of gallium that we would form in the reactor. So we started with polycrystalline gallium crystals. They were about 50 to 200 microns in diameter, and they were then exposed to hydrogen. And what happened is shown here in the SEM. These large gallium grains were totally eaten up by in the reactor, and what you're left with is just some remnants of the gallium precursor, and again some reduced gallium droplets. But the nice thing was, now we have a very strong control on the source of gallium in the reactor. So after the hydrogen plasma runs, now we expose these droplets again to a hydrogen-oxygen plasma, just like it was done earlier to form these single crystal nanowires that you saw, the ones that look like the hedgehogs. And now what happened is we formed 2D networks instead of forming these bushels or round droplets that were overgrown with, looked like grass growing on droplets. Here you can see little wires, they're necking, they're forming overall a web, and I've enlarged this for you just so that you have a little bit of a better look for that. This is what we now termed a nanoweb, and I'm going to show you all the details within this web, but just to give you an idea of what I'm talking about in the title. 2D because it really spreads two-dimensionally over the surface, and these are individual wires and tubules that self-assemble into a network structure. And in order to show that, I'm going to focus in on this area here. Overall, you have a wire density on the order of 10 up to the 9 per centimeter square. This is tremendous for any electronics applications, for example, or fuel cell applications later. I'll show you, John. The little round area that I had highlighted shows now under much larger magnification what's really going on there. We're not only having wires, we have tubes. Actually something that at first reminded me of a carbon nanotube. but this is a oxide nanotube of gallium oxide, and you have the d-spacing, 3.67 Armstrong, is corresponding to the 201 planes of the beta gallium 203. This is just another example now, where again you have a tube. This is semi-hollow in the interior, and again the d-spacing is 3.67 Armstrongs across. So if you look at these tubes, they have something that characterizes them that's a little bit different from the carbon nanotubes. For example, you can see that they have a very sharp tip in the cap, and almost like a sharp angle on the like something that's already forming a planar surface. This is very, very interesting for applications such as, for example, Schottky junctures, NP-type Schottky junctures, which would be very important for nanoelectronics. This is another example, a little bit more random here. You don't have the very nice structures, but again, you can see the wall formation of these tubules. These are just a TEM and a SEM juxtaposed. Here I superimposed the alignment of the nanowires, and you can see it's not very structurally regular, but overall it is regular enough to form a network structure, a 2D network structure on two-dimensional covering the surface. In the TM, we can still pick up the web-like structure, and you can see that these are polycrystalline materials. The X-ray data indicated that if we are now comparing the nice nanowires that I showed you at the very beginning, that had the nice elongated shape and needle shape, they had really clearly good X-ray peaks, but the nanowebs have peak broadening effects, and that simply comes due to the fact that all the structures in there are extremely in the nanoscale. We felt that we should do one other experiment to just see what would happen if we would take these nanowebs now and would resubmit them to a hydrogen plasma. In other words, now you have these arrangements, two-dimensional arrangements of wires. What would happen if we would re-expose them to a hydrogen plasma and then again a mixed plasma? And this is what the result was. Instead of forming the tubular structures, now we're forming elongated single crystal structures, but again with a very sharp tip in the cap. We were just looking at a bulk material of the nanowebs, just to see if we could find some reduced oxide species in there. But for 3 samples, we really felt that the majority of the sample is in the gallium 203. There is a slim suggestion that there's some reduced gallium, but and obviously there is just the metal present in the sample. But the majority of the material on the entire sample holder was gallium 203. The next step really, in order to be able to harvest these type of materials for catalysis, is to really understand what the mechanisms are that form these materials, so that we can hopefully manipulate them further and then extend that to other oxides. Oxide that might be interesting for fuel cell applications, such as cerium or titania for, let's say, for self-cleaning purposes, or for water splitting to form hydrogen, for example. So to understand the mechanism is critical. So we feel that there are actually 6 steps, and I want to go quickly through those, not to spend too much time on that. But at first, there seems to be, it's very critical that you have the reduction of a precursor polycrystalline grain, and this occurs in the reactive hydrogen. Next comes the formation of these nano-sized gallium droplets, and that is the most critical aspect, and I'll go back to that. Without having had the opportunity to form a thin film with only selected, very individually placed gallium, nano-gallium droplets, we would have formed again these larger structures, or the ones that look like you know, the hedgehogs. And then certainly the formation of a gallium thin film will allow these droplets to flatten out. And this is simply because we bring in the mixed plasma, and then you basically have something that we termed it wetting of the surface, and the droplets flatten out, and you basically end up with something like a small gallium disc, and that's important later for my mechanism. So what's really critical is to use a hydrogen plasma to reduce polycrystalline gallium oxide particles, and to really make sure that the gallium droplets stay in the nano size. This is just one image, an SEM image actually, to show you the surface of one of the gallium droplets, and I chose a very large one just to show you the features better. Most of the gallium droplets are actually much smaller than a micron. This one here is actually huge. It's 2 microns, 2.5 microns across. But it shows what's happening on the surface. When the gallium droplets form in the mixed plasma, you form a very, very thin skin of oxide layer on the gallium droplet surface, and that prevents the droplets to coagulate and to form larger droplets simply by coalescing together. And that's very critical. So in the nanoweb formation mechanism, you then have the gallium surface, you bring in reactive hydrogen oxygen again, and you reoxidize the surface, which actually were these thin discs. That's why I pointed out to you that these droplets thin out and forming discs. And each one of those discs now is the host, or the start point, for wire formation. And you can have several wires, up to 3, 4 wires formed from one of these small discs. And until the gallium is depleted, you will be able to have wire formation, or until these wires will finally meet, and then also that will determine the length of the wire's growth. We can see in the SEM actually that the wires approach each other, but actually in TM you see it a whole lot better. This is just to highlight what we think is happening on the atomistic scale. The gallium droplet in the mixed plasma, you have on the molecular level oxidation, reduction reactions occurring over and over, and gallium atoms will be able to migrate this way, will then be oxidized and be fixed at the surface, and new ones will come back, and so you will have growth this way, as well as in length as well as in width. So a number of factors we feel will contribute to this, to the length and the thickness of the wires of a nanoweb, and that is very important if we want to control the morphology of these wires. If we want to control a surface that is covered by nanowires, that we might be able to let's say, put between an electrolyte layer and an anode layer of a solid oxide fuel cell. So as one of the very important factors we feel is the ratio of reductant and oxidant in the gas phase of the plasma, obviously, the ratio. The next one would be the concentration of the reactive hydrogen atoms produced in the plasma. The temperature, of course, is very, very critical. I didn't mention that, I forgot. The temperatures of these experiments were 550 degrees Celsius. And the controlling of the surface diffusion rate of the gallium atoms, obviously, is very strongly dependent on the temperature, and therefore also the resulting nano wires or nano tubes. And finally, the size distribution and the density of the created gallium droplets, that will depend on how we start the experiments, what types of precursors we use. This is now one step further to show you if we use a larger amount of precursor, we can actually extend the webs. Now they're no longer nanowebs, they're networks, over various dimensions, micron sizes. We actually were able to cover centimeters of a quartz glass plate. And the most interesting part is that the layer thickness was still so fine that it was totally transparent, the glass. So there are lots of interesting opportunities to use catalytic properties on glass surfaces. This is 1.5 microns for those of you in the back. The image that I just showed you, let me backtrack one. You can see right here there's a defect actually, but what it shows very nicely is that we have layer by layer growth, and that is shown here systematically here. The first layer would obviously be the layer of gallium droplets, juxtaposed to it the first layer, or nanoweb layer I call it, and then it can be coated by a second nanoweb layer. And we would like to learn how we can get a control on how thick we can make this layer, and how the surface area of these layers is, and how it affects the possibly even interconnectivity. But if you look now, this is just a computer simulation showing 15 nanoweb layers superimposed. And where I see this may become important, for example, this is a solid oxide fuel cell. It hasn't been shown this morning in this aspect. You have the ion conducting the electrolyte, and you basically would like to have a layer here where you would be able to still have ion conduction but no electron conduction. So we think that we might be able to get some serial nanowebs produced. That's our next goal anyway. And also TiO2. So to just summarize this, there is a lot of work that needs to be done to understand the catalytic properties of these nanowebs, but I think they have tremendous opportunities for us. Surface area of these materials, we found the gallium oxide nanowebs had surface areas of 143 meters square. Excuse me. And so there could be possibilities for Syria, especially since Gary showed this morning that surface area is a very critical aspect. The spatial extent of the fabricated nanowire network that we showed for the gallium was only limited by the substrate dimensions, the reactor dimensions, but we think that with the plasma torch we might be able to cover large surface areas. And there are tremendous opportunities we would think are, just to give you an example, for windshields, self-cleaning purposes with titanium. And there is finally the plasma fabrication route offers the possibility of achieving tremendous wire densities. 10 up to the 9 was what we found for the gallia. We don't know what it would be for other metal oxides. The first one that makes sense are zinc oxide. These experiments are underway. So is tin oxide. But the one that we feel is the most promising is the titanium. And if you have questions, I'll be happy to answer it.
I'm assuming that you are going through solid and liquid phase transformation. So how would it apply to solid metals?
Say again?
You have to go through the solid liquid phase transformation.
How to do it with
like you suggested, titanium.
That's a very low melting metal, yeah.
Right.
With the titanium, we, instead of having to start with the very large, gallium, we used 200 micron size precursor polycrystalline gallium oxide grains, and for the titanium we're using actually diffuser spherical nanoparticles around the 10 nanometer range. So we basically sidestepped that one critical step, or the one that we found was extremely critical, to have the droplets on a very nice thin film arrangement. And then the other nice thing is we don't have to worry about equality like the gallia does. The gallia is very special that way. Yeah, copy?
It is my understanding that when you use gallium oxide precursor to break it up into gallium droplets by exposing it to hydrogen plasma. Instead, if you put a film of gallium and then expose it to hydrogen plasma, you would still be getting gallium droplets.
Right.
What was the rationale in using gallium oxide precursor?
The gallium pools, you could try to distribute the gallium pool in a very, very simple way, like with a doctor plate. But the tendency of the gallium to just kind of, come together in one spot and kind of form one large droplet was so strong. And that was the main reason for me to decide to start with particles where just by looking at the first SEM that I showed, you had a lot of gallium forming on the nanowires. I felt that if that happens, then it should also reduce the gallium oxide and form in situ gallium droplets on the gallium oxide surface. And I would have been happy if they had just formed on the gallium oxide surface, droplets sitting there just like you saw on that eroded grain. But the nice thing that happened, and we didn't expect it, but it was a bonus, that was that nano-sized gallium droplet formed evenly over in the background. And they didn't grow, simply because that was when you start out with the gallium oxide. And I'm not claiming that I did this because I thought of it. It just happened to be very beneficial. There was enough, obviously, oxygen released when the precursor gallium oxide grains were, reacting in the hydrogen plasma, that it allowed the small nano-sized droplets to be coated with a very thin oxide skin. And I showed that one larger droplet simply because at the SEM the resolution is so bad at the small droplets you wouldn't see it, but also the small droplets have that. And there is actually a very good paper available. I can give you that. That shows that that oxide skin is extremely critical to keep the droplets from growing. And that's why, Narash, I would think that was our thinking, going to using nano-sized precursor instead of the micro-sized precursor for the for the metals that are not that, winnable like ours. Aaron?
What do you think the effect of dopants would be, or what I'm going towards here is, could you make superconductors with this material? Because forming wires out of superconductors is the hardest part.
Yeah, well, there are like two people at MIT that are very, very interested in the, basically the same idea that you have, and they looked at the sharp tips, and if you could dope them and keep the Schottky junctions, you would have, tremendous opportunities in electronics. At that small scale, I don't know how to, to control it. If we start with the doping, we need to find out how evenly it will be on the wires. And that's why I said at the end of the talk, this is just a whole new area that's opening up. It should be done. We haven't doped them yet. But especially if we are looking at titania, and I hope we'll be able to form webs with the titania. In that case, they need to be doped. And so that would be the very next step. No, that's a good question.
That was the last question. No, John.
Are there specific properties in an element or an oxide that this is constrained with, or do you think this can be applicable to a broad range of different oxides?
You mean the wire formation? We think that it should be extended easily to the zinc oxide and tin oxide, but titanium may be more difficult. And that's what I'm really after, but for water splitting. But right now we're going the easy route. We're trying the tin and the zinc first, and they form nanowires very, very nicely. So whether or not they will form the web formation has to be seen.
And a follow-up, when you made the layers, was that in multiple steps, or did it just?
Actually, no, it wasn't, but that's a really good observation. We just used a larger amount of precursor, and so you had more source for the wires to form. I think at one point you run into trouble because then you form the hedgehogs again. So it's a very critical, like, you know, you're at this end and you have perfect nanowebs, and then here you have the hedgehogs, and then anywhere in between you may end up with layers. Right now it's really not a science yet. It's still you know, trial and error. But what impressed me the most was the hardness of the wires, the oxide, like you know, forming a ceramic. You cannot scratch the glass surface, and it was so hard to even get samples for the TM. I mean, it was like at first I didn't even know what I could do, and only the sample that had more layers, then the layers chip off easy. But the first layer is tremendously hard and totally transparent. So there are possibilities for optics such as tin oxide, which has a much better transparency than gallium.
Okay. Oh, okay. Last question is the.
I guess that how the gallium spreading determined by also the interfacial energy between the gallium and the substrate. What's the material substrate? What's the purity of
the substrate? The substrate was quartz glass. I would have to look it up right now to be sure what the purity was.
It's a highly pure quartz.
Yeah, but I do want to tell you something else. Everywhere where the glass had scratches, whether the scratches were on there accidentally or I scratched them on purpose later, the gallium droplets would form preferentially in the scratches. So there is a suggestion that you might be able to help direct the growth where you would like to see it. And I think that has to do with the basically the gallium will have three sides to attract to the droplets, and then once the oxygen comes in, that's where the webs form. So you may be able to form bridges.
Okay, thank you very much.